bit of work with trig substitution. So you're going to use trig substitution in the case where you have an integral containing a square root of the form some number plus or minus x squared, or x squared plus or minus some number. Okay? Now, this is sort of one of the worst sections in the unit, just because there's a lot of things that you have to take care of when doing one of these problems. But I've tried to outline it in a way that you don't really have to memorize it, and you can just follow along with your intuition and try to figure it out as you go. So basically, you're going to see one of three forms. Number one is some number minus x squared. Number two is some number plus x squared. Number three is x squared minus some number. They're all, of course, under the square root, but that's the form that they're going to take. Now, you can memorize what substitution to make when you're faced with different forms, but I would advise against it just because it's really easy to forget it. It's much safer and better practice to understand what's going on and the motivation behind each substitution in order to actually be able to do it yourself. So when you have some number minus x squared, the idea is that if you substitute a sine theta, where a is basically the square root of this number, this is what's going to happen. Watch very closely. So if you have a sine theta substituted for x, then when it gets squared, it becomes a squared sine squared theta, and then we can factor out an a squared, and we're left with a squared times the quantity 1 minus sine squared theta. Now, 1 minus sine squared theta can be written as cosine squared theta, and then we have a squared times cosine squared theta, and then we can just remove the square root easily and just write a cosine theta, right? That's basically the approach for all of them, except we take advantage of different trig formulas, trig identities for each different case. For example, here we know we're going to be left with a 1 minus cosine squared theta. And we know that there's an identity sine squared theta plus cosine squared theta is 1. So that makes it perfect. Here we can tell if we make the correct substitution with the correct scalar, we're going to be left with 1 plus something squared. Now, if that something was tan, then it'd be 1 plus tan squared, which is secant squared. So that solves our problem here. And then here, where we have something squared minus 1, again, after we factor out the a, we're going to have, something squared minus 1. If that something were secant, then it would be secant squared minus 1, or tan squared. And we can take the square root away, again, as easily. So that's really the approach that we're going to take. Let's do an example and see how this is going to play out, because there's a little bit at the end that we have to do after this process is finished. So here we have square root of 9 minus x squared over x squared. So I'm going to ask myself, well, if I do the substitution correctly, what am I going to be left with? I'm going to be left with, if I, again, factor out the a, I'm going to be left with 1 minus some function squared. Well, if that some function were sine, then it'd be 1 minus sine squared, or cosine squared. So that's the substitution I'll make. So I'll say x is equal to, now, choosing the a must be done right. If you choose the wrong a, you will run into problems. So we have to be careful. I want an a so that when it gets squared, it gives me 9. So I'm going to choose 3. Very simple. It's 3, and I'm going to choose sine. Again, because when I actually carry it out, I'm going to get cosine squared. So what's my dx? Well, dx is going to be 3 cosine theta d theta. All right, so let's actually go ahead and do the substitution. This is equal to 9 minus 9 sine squared theta all over 9 sine squared theta, and then dx gets replaced with 3 cosine theta d theta. Let's go ahead and clean this up a bit. Now I can factor out a 9. 1 minus sine squared theta over 9 sine theta, and I still have my 3 cosine theta d theta. And as you can see, the 1 minus sine squared theta pops right out. And we can say, okay, well, it's going to be 9 times sine squared, or cosine squared theta. And then I have my 9 sine theta and 3 cosine theta d theta. Now I can remove the square roots, and I'll have 3 cosine theta. And the 3 and the 3 go with the 9. And I'm going to be left with cosine squared theta over sine squared theta, or cotangent theta squared theta d theta. Now, we're not done yet because we don't exactly know how to integrate cotangent squared theta. But we do know how to make it a little different. Just because we don't know how to integrate cotangent squared theta doesn't mean we don't know how to integrate other trig functions that are related to cotangent. So what we're going to do is exactly how we got this formula from this formula. We divided everything by cosine squared, right? Now we're going to divide everything by sine squared and see what we get. If I divide this by sine squared, I'll get a 1. If I divide this by sine squared, I'll get a cotangent squared theta. And if I divide this by sine squared, I'll get a cosecant squared theta, right? So now I can rewrite my cotangent squared theta as cosecant squared theta minus 1. So cosecant squared theta minus 1 d theta. Now this I can integrate, right? I can say cosecant squared theta is just the antiderivative to minus cotangent theta. And minus 1 is just the antiderivative to, cosecant squared theta is the derivative to minus cotangent theta, and 1 is the derivative of x, or theta. So, and don't forget your plus c. All right, so is that it? No, and this is one of the worst parts of the process. So now we have the answer, but it's in terms of theta. We can't report the answer back in terms of theta because that was a made-up variable. So we have to go back to the place where we made it up and figure out the relationship between theta and x so we can report the answer back as x, or in terms of x. So if you remember, the easiest way to go back to the relationship that we created with that statement is to draw the triangle that statement represents, okay? Otherwise, the algebra is just too complicated. So what we're going to do is draw the triangle, the right triangle that statement is describing. It's saying x is 3 times sine theta. So I'm going to draw a right triangle with an angle theta, and it's saying, look, if 3 were my hypotenuse, so I'm going to place it there, and I multiplied it by sine of theta, so this, I'm going to get x. So x is going to be here, right? 3 sine theta is x. If it were cosine, I would have said 3 cosine of theta, and x would have come here. Okay? So what is this side going to be? Well, it's just going to be 3 squared, or 9, minus x squared. Okay? So what I need to figure out is what cotangent theta is in terms of this stuff, and what theta is in terms of this stuff, and then I'm done. So cotangent theta, and what's cotangent? It's cosine over sine, right? Cotangent theta is cosine over sine, or in other words, I'm going to leave the minus sign. It's 9 minus x squared over x, cosine over sine. Then it's minus theta, and what's theta? Well, theta is just, it's easy to get it from right here. It's inverse sine of x over 3. We just solved that equation for theta. So inverse sine of x over 3, and then plus c. And there you have it. That's your answer. As you can see, it's not a very pretty, this whole section is not that pretty, in my opinion, but it's something that you have to learn. And if you can work through it without memorizing it, which I highly suggest, it's much easier than the alternative. So there you have it.